All right, so here we are with our 1-2 assignment. Here's some slides that I will go through each of the problems. The answer key solutions are also on HeadRush, so you can just look at that to double check your answer before you want me to work it through it. But either way, here I am doing all the assignment questions. All right. So in number 2, the directions are to determine whether the formula determines y as a function of x. And so, again, we're trying to find out, in this case, if it passes the vertical line test, basically. So what's happening here is that this is just shorthand for two equations at the same time. So this is actually a system of x squared plus 3 and then x squared minus 3. Now the problem with that, of course, is that you now have two equations, and two equations would end up with two different y values. For instance, if I put a number in for this x, like 2, I'd get 4 plus 3, which would be 7, and then if I put in a 2 down here, I'd get 4 minus 3, which is 1. And so the problem is that if I put in a 2 for my x value or my input, I'm going to get two different outputs. And so that is not going to work, and so it is not a function. Whoa. I'm using a very old school stylus, so I'll be getting a new one soon, but that is not a function. Okay. The next part here is number 4, and so if we take a look at that one, you'll notice that they have written it so that it is not y equals, so we do want to take the time to rewrite it. So this positive 12 is going to move over to the other side, and now we realize that we have x minus 12 equal to negative y, but of course we're going to take out that negative, and so really we have the linear equation negative 1x plus 12. And so since that's linear, turns out all linear equations will pass the vertical line test, and so we're going to say yes, it is a function. And so again, the idea here is that the formula determines y as a function of x is literally the asking, is it a function? So just terminology, and then you're going to say, well, why didn't they just ask that? And that is because you're supposed to know how to translate that. So there we go. All right, the next one's here. We're going to use the vertical line test to determine whether the curve is the graph of a function. So definitely can see right away that this one is a function. I'm going to just write func, okay. The next one here, if I draw a vertical line, definitely going to touch it twice here, so definitely not a function because it doesn't pass the vertical line test. The next one is going to be not a function as well, because it's going to intersect twice. And then this next one here, it's a little bit hard to tell, but you do actually have this equation going up in these pieces. And if you remember back to Algebra 2, this is an asymptote of a ratio function. And so we do have an asymptote, and so that will never actually touch twice at that point. So this is actually, yes, a function. Because if you don't know about those asymptotes, then it makes it look like maybe the one on top will cross over with the one on bottom, but they will not. So it is a function. Asymptotes, vertical asymptotes at least, are totally fine. All right. And then they want you to find the domain of the function. The easiest way to find the domain, and that is the way that I will be doing it, is by graphing. Okay, so we did actually have in Algebra 2 a way of saying, oh, well, if the denominator makes a 0, because that would be bad, at 3, then we can't include 3 in our domain. So there were different ways of kind of working through this without just graphing, but the best idea would be to learn how to type it into your graphing calculator and then graph from there. So into my y equals for number 10, whoops, I'm going to type in, let's see, Ooh, I've got some extra equations in my calculator. All right, so I'm going to type in 5 and then the fraction bar. And depending on what version of the calculator you have, if it makes fractions, that's cool. But otherwise, old school here, we've got 5 division sign, parenthesis, x minus 3 division sign, or sorry, close bracket. So that is what I'm typing into my calculator, and if you go to Zoom Standard or Zoom number 6, you'll get kind of a general gist of a 10 by 10 graph. So if we take a look at this 10 by 10 graph, which is kind of what I already determined in that shortcut idea, is that we're going to have this happening in a little asymptote. And of course that asymptote is happening at the number 3 because that was what would make that denominator 0. So in that case, the domain of the function is going to be all x's that go from negative infinity, so that's over here, but then stop at 3. So we don't include infinity, we're talking about x's, and we don't include the number 3. And then we're also going to be talking about then the numbers from 3, including of x's, including positive infinity, because that's going to go over here. So this is the standard way of writing this. Technically, you would be putting these both in parentheses and then have kind of like a union going on of both of them, but we do not need to be that technical. The best way to do this is just writing your inequality that tells us what the domain is. All right, so the next one, again, we could have determined that x of 0 is bad because it makes a denominator of 0, and then also an x of 3 is bad. And so there are going to be in our domain those two numbers that don't work. But visually, it's a lot easier to understand what's happening. So I'm going to do that and that divided by x minus 3. So the interesting part with your calculator, of course, is that you do not have a lot of options when it comes to what to type in to make it a fraction. So what I've typed into my calculator for number 12 is y equals, and then in parentheses, because I want to make sure it's all by itself, 1 division sign x, and then plus parenthesis 5, and then division sign parenthesis x minus 3. And again, that's because, and you gotta finish that one, there we go. So that's why I typed into my y equals so that I could graph this appropriately, because you do not want to forget any of those grouping symbols that would be around each of the fractions, denominator and numerator, as well as each of the fractions. Otherwise, you're going to end up with a different picture, and then you're going to wonder why 0 and 3 didn't work because it did on yours. So officially, the image that you would be looking at is an equation coming in to 0 at this part, and then a little cubic function looking thing, and then another one coming out here. So lots of stuff happening, but we know that this is at 0 is an asymptote, and then we also know that at 3 would be your asymptote. So the domain, as it was before, comes from negative infinity, stops at 0. So we're going to kind of have a lot of pieces to this inequality. So negative infinity is where our x's are, but then they stop at 0. Then from 0 to 3, we're still existing. And then from 3 to infinity. And so that's your domain for that. The next one, this is where we get into, again, determining if something works or not. And so in number 14, the denominator, as we've seen already, can't be 3, right? That's not a good number for the denominator to be 0. But then also anything that's inside of here that makes a negative number is not so good either. And so there will be an entire strain of numbers that won't work. So visually, again, it's a little easier to see. Whoops, I was trying to erase. See what's happening. So if we type this in to the calculator, you've got your square root and 4 minus x squared. That's not a 4. 4 minus x squared and then division sign, parenthesis x minus 3. All right, so what I've typed in my y equals, as I showed before, is parenthesis and then square root, and then in the square root, which automatically groups it, I put 4 minus x squared, and then I have the fraction bar, and then in parentheses x minus 3. And again, if you don't have this set of parentheses, it ends up just taking this and dividing by x, and then in the end subtracting 3. So order of operations is very key here to make sure that we get the graph of what we actually want. So the graph of this picture is really weird. Okay, so it looks like, I think that's an asymptote, but I need to zoom. Yep, so basically starting at the number -2 and then going to +2, it has this kind of graph. All right, so that's interesting. So another thing that's not necessarily, visually, the denominator can't be 3. Well, clearly that's not even in here. All we have is from -2 to 2, and that's because of this guy right here. Because any time that you would put a 2 in here, you'd get 0, and then anything greater than 2 as well, because you'd be subtracting, you get a negative number, which is not good. So it's just this kind of smiley face looking thing here, which means that our domain is only going to be between 2, and it looks like it includes 2, because 0 is a number, and then also includes -2. So your domain is all x's that are between -2 and +2, and then you always have less than symbols. Oh, and then equal to, because we said it includes 2, because it's not an asymptote. All right, moving on to number 16. We're going to do x to the 4th. That is interesting. So going back to your y equals, we're going to type in a parenthesis, a square root, and then an x to the 4th. And since there isn't an x to the 4th, depending on what year calculator you have, as long as the calculator puts the 4 up here, you don't actually need a parenthesis. Of course, the calculators like TI-83 would have you actually do a caret and then a 4, and so because there's a caret, you do actually need to put parentheses. But if you're using something like the online calculator, you will not need to do that because it'll make the tiny little 4. So we've got x to the 4th, and then we'll subtract, but make sure you're still inside the square root. Subtract 16x squared, and then that's that. So our picture is basically supposed to be a kind of W shape, but what happens is at -4 and 4, it actually gets eliminated. So -4 is actually more like here. And so this part of the graph is actually eliminated, because if you plug in any of those values down here, that would appear down here, you end up actually getting a negative number. So if you plug in a -3 or a -2 or a -1, you're going to end up with a negative underneath the square root, which is not allowed. And so in that case, because it's going from -4 to 4, that we can't do, I wonder if 4 does actually work. I bet it does. Yeah, 4 is still 0. So that means that we can include 4. So from -infinity to x, including the number -4. And then from +4, including it, to infinity is our domain for this one. And again, all you're looking to see is what x's work. So going in from the left, these all are working because this kind of goes on to infinity here. So all of the x's will get you a point until all of a sudden -4 gets you 0, and then everything else doesn't exist until you get back to 4, and then all the way on to infinity. So that's what this is saying. However, it's so much easier to just say the numbers between -4 and 4 don't work. But that's what that's why we're learning the math so that we can say it in a way that everyone can interpret. So, next one here, they want you to find the range. So remember that the range are the y values, and so now when we look at our picture, like the previous one, we'll actually be looking at, for instance, from positive infinity to 0, or whatever number it stopped at. So we're looking at up and down, what works. So typing in, again, into your calculators is the fastest way to figure out what works and doesn't work. But again, generally you're looking for these square roots or denominators and things that will make it 0 or negatives. So if we type in 5 plus the square root of 4 minus x and graph it, all right, we get this kind of logarithmic looking thing here, and it does stop at 1, 2, 3, 4. Let's go to the table. It stops at 4, 5. So this point right here is 4, 5. Okay, and so as we look at that, and we're looking at the range, so not the domain, we have, thinking of the lowest number that it goes to, the lowest number that the range goes to would be 5. And it is including that 5. And we're talking about y's. And then from there it goes on to infinity. So anytime you're doing these inequalities, you're always looking for the lowest value and then the highest value, which of course can be infinity if it needs to be. All right. Then in number 20, we are trying to graph, and of course putting parentheses around the numerator and denominator, otherwise you will not get the right picture. And and parenthesis, division sign, 4 minus x squared. All right, so if we graph this picture, take a look at what y values are working. You've got an asymptote coming here and then down. There's a little bit of a parabola there, and then coming up here. So taking a look at what's happening here, the lowest point, oh, I drew that badly. Turns out that the lowest point that this graph gets to is at 1. And then apparently between 1 and 0, but maybe it's a -1. Let's check. Table. I'm just trying to figure out if this asymptote is at 0 or if it's at -1. And so if I go to the table, I can see that it approaches -1.01, getting really, really, really small, and never actually going to -1. So it turns out that between -1 and +1, this is kind of a dead zone in here. And so that means that when we talk about the domain, and in this case range, the range, yes, does include -infinity and does include positive infinity, but it's also two different surrounding values. So from -infinity to -1 exists when we talk about the y values. And it doesn't exist at 1, -1, so we're not going to put an equal to sign there. And then it starts up again at 1 and goes to infinity. So again, reading this, the y values exist from -infinity all the way to -1. They stop and don't exist until the number 1, and then they go on to infinity. It's kind of like, what are the possible range of answers for that visual? All right, so the next few example or questions here want you to graph the function and tell whether or not it has a point of discontinuity at 0, so meaning is there an output from putting in 0? And if there is discontinuity, tell whether it's removable or non-removable. So technically in this phrase, you can look up exactly what they're talking about here, but basically they're just saying to identify it. So is it asymptotal? Is it jump discontinuity? Is it point discontinuity? Those were all the pieces that we went over in the notes yesterday. So, or whenever it was that you listened to those notes. So in number 21, we're looking for 3 divided by x. And just as I did in the previous ones, I'll go ahead and graph and show you kind of a sketch of what's happening here. Sorry, my pen is not working. All right, so in a very standard 10 by 10 grid, what we're looking at here is, wow, what is that, 3? Oh, it's stretching it, so that's why it's taking forever. Weird. What did I type in there? 3 divided by x. Okay. It was doing something weird for a minute, but here we go. All right, so turns out that it comes in here and comes in here, and we have an asymptote here and technically right here. So, answering some of our questions here, graph the function and tell whether or not it has a point of discontinuity at x equals 0. So if we take a look at x equals 0, there is an asymptote, and so we are discontinuous, meaning you picked up the pencil, and so it's going to be asymptotal discontinuity. So that's number 21, because an asymptote exists at the x of 0, which would be, right here. All right. Next piece, again, remember that there are parentheses around numerators and denominators to make sure that you graph the right picture. So x to the 3rd plus x, parenthesis, division sign, x. Okay. So this image on a 10 by 10 grid, it looks pretty much just like a parabola, but of course there's things happening. In fact, I can already tell that there's going to be a problem at 0 because a denominator of 0 would not work out so well. So if you go into the table versus into the graph itself, you'll notice that it does give you 0 for x and an error. So that actually means that if I drew this really accurately, I'd have a open dot at 0. So it would be completely continuous and except on that. And so we're going to call this point discontinuity. All right. So again, this removable, non-removable is not really what we're looking for. It's more about the type of discontinuity. All right. So the next one is a little bit different because this is your absolute value. And if you're not really familiar about where that is in your calculator, it's under the math key, and then it's under the column num for number, and then it says ABS. So what it will look like in your calculator is ABS parenthesis x, and then you'll have division sign and then x. So that's what you'll type in to your calculator. So math, absolute value of x, and then division sign x. And again, it depends on what version of the calculator you have, because you may actually have a set of parentheses show up, and then you could put your x inside. So absolute value parentheses there. Okay, so again, just like the previous one, you'll notice that there is a denominator of x, and so we will have some interesting version of whatever's happening at 0 here as well. So taking a look at our picture, don't know why I deleted that. Oop. Typing too many things at once. All right, here we go. Okay, this is a fun one. You're going to have a completely horizontal line at -1, and then a completely horizontal line at +1. And it turns out that, especially if you check in the table at 0, you do have open circles because we have no point at 0. And so looking for if there's a point of discontinuity, you say that there is point discontinuity. Or actually, jump would include it. So either way, point or jump discontinuity. Actually, now that I think about it, definitely jump, because you don't end up following that continual line as the point was removed. You have to change where the line is. So it is jump discontinuity. And then the last piece, again, parentheses for your denominator. And taking a look at that denominator, what's going to make it 0 is if you plug in a positive 2. So typing this in, our image is going to come in here from the side and go through there, and then come in here and go there. So there is an asymptote at the number 2 for vertical asymptote, and then there's actually a horizontal asymptote as well at the number 1. All right, but if we look for discontinuity, well, actually I need to know about what happens at 0, don't I? Oh, 0 is 0, and so there's only an error at 2, and so in this one, we just, at x equals 0, there isn't any discontinuity. So no discontinuity at x equals 0. There is discontinuity at 2, but they didn't ask us that. They asked at 0, so there you go. Kind of a trick question, but not really. All right, moving on. Let's see. I think I'm going to run out of time on this video, so yay, 2 homework videos. Okay, so taking a look at number 25, we're supposed to state whether each labeled point identifies a local minimum or a local maximum, or in fact neither. So we need to identify intervals on which the function is increasing and decreasing. So I don't usually go over increasing and decreasing all that much because it's pretty apparent if something is increasing or going up or a positive slope, or if it is going down. But for some reason, we tend to forget what's going on. So I do want the word slope here. Wow, I really keep trying to press the eraser there. Okay. So taking a look at what we have here, a positive slope is going to go starting at negative infinity here all the way up until that point. But then, of course, it's starting to go down, and then it starts to go up to the next maximum, and then down. Okay. Same thing happens for this next one here. We go down until we reach that point, and then all of a sudden we go up, but then we still go up, and then down again. So when you're looking for figuring out your increasing and decreasing, for this one here, for decreasing, you would say, okay, from this point here to this point here, we have from an x of -1, and you can't actually increase or decrease on a point, so just -1, not included, all the way to 2. And then if it helps, it's easier if you just kind of erase this second point, because you're really only looking at the x's when you think about the points that are involved in our inequality. And then it's also decreasing from 5 to infinity. Over here it's decreasing from negative infinity to the number 1, and then from 5 to infinity. For increasing, again, you're going to do the other piece, but as I said earlier, it turns out that we have run out of time for my only allowed half hour for recording. So I'm going to stop the recording, and if you want to go over anything more than number 25, you'll just go to the next video.